Welcome to our deep dive into the fascinating world of haloarenes in organic chemistry. Haloarenes, also known as Aryl Halides, are aromatic compounds where one or more hydrogen atoms of the aromatic ring are replaced by halogen atoms. These compounds play a significant role in both academic research and industrial applications. In this video, we'll explore their structure, methods of preparation, chemical properties, and their importance in various fields. Whether you're a student or just curious about chemistry, this journey will help you understand why haloarenes are so essential. Let's begin by understanding what makes haloarenes unique compared to other organic compounds. Haloarenes are aromatic compounds in which one or more hydrogen atoms attached to the benzene ring are substituted by halogen atoms such as chlorine, bromine, or iodine. This substitution imparts unique chemical and physical properties to the molecule. The presence of the aromatic ring and the halogen atom together creates a compound with interesting reactivity and stability. Understanding the basic definition of haloarenes sets the foundation for exploring their behavior in various chemical reactions and their applications in real-world scenarios. Structure of haloarenes is based on the benzene ring, a 6-carbon aromatic system with one or more hydrogens replaced by halogen atoms. The halogen atom is directly bonded to the aromatic ring, which influences the electronic distribution within the molecule. This structural arrangement affects both the physical properties, such as boiling and melting points, and the chemical reactivity of the compound. The position of the halogen on the ring can also lead to different isomers, each with its own set of characteristics and uses. Haloarenes can be classified based on the number and position of halogen atoms attached to the aromatic ring. Monohaloarenes have a single halogen atom, while dihaloarenes and trihaloarenes contain 2 or 3 respectively. The position of these halogens, ortho, meta, or para, also leads to different isomers. Each type exhibits distinct physical and chemical properties, which are important in both laboratory synthesis and industrial application. Recognizing these types helps in predicting their reactivity and potential uses. Some common examples of haloarenes include chlorobenzene, bromobenzene, and iodobenzene. These compounds are widely used in the synthesis of dyes, pharmaceuticals, and agrochemicals. Chlorobenzene, for instance, is a key intermediate in the production of phenol and aniline. Understanding these examples helps illustrate the practical significance of haloarenes in everyday products and industrial processes. Haloarenes generally have higher melting and boiling points compared to their parent hydrocarbons due to the presence of the halogen atom. They are usually insoluble in water, but soluble in organic solvents like ether and benzene. The physical properties such as density, refractive index, and color can vary depending on the type and number of halogen atoms present. These characteristics are crucial for their identification and separation in laboratory settings. There are several methods to prepare haloarenes, each with its own advantages and limitations. The most common methods include direct halogenation of benzene, the Sandmeyer reaction, and the Gattermann reaction. Each method is chosen based on the desired product and the specific halogen to be introduced. Understanding these preparation methods is essential for both academic study and industrial synthesis of haloarenes. Direct halogenation involves reacting benzene with a halogen, such as chlorine or bromine, in the presence of a Lewis acid catalyst like FeCl3 or AlCl3. This method is straightforward and commonly used in laboratories. The reaction leads to the substitution of a hydrogen atom with a halogen, forming a haloarene. However, this method is not suitable for introducing iodine due to its low reactivity with benzene. Sandmeyer reaction is a versatile method for preparing haloarenes, especially when introducing chlorine, bromine, or cyanide groups. It involves the diazotization of aniline followed by the reaction with copper, I-halide. This method allows for the selective introduction of halogens into the aromatic ring and is widely used in the synthesis of various aromatic compounds. The Sandmeyer reaction is particularly valuable for preparing haloarenes that are difficult to synthesize by direct halogenation. Gattermann reaction is another important method for synthesizing haloarenes. In this reaction, benzene is treated with hydrogen halide and a Lewis acid catalyst, such as AlCl3, in the presence of copper powder. This method is particularly useful for introducing chlorine and bromine into the aromatic ring. The Gattermann reaction provides an alternative to the Sandmeyer reaction, especially when working with specific substrates. Finkelstein reaction is a halide exchange reaction used to prepare iodorenes from chloro or bromorenes. In this method, the haloarene is treated with sodium iodide and acetone, leading to the substitution of the halogen atom with iodine. This reaction is particularly useful for synthesizing iodorenes, which are otherwise difficult to obtain by direct halogenation. Haloarenes exhibit unique properties due to the presence of both the aromatic ring and the halogen atom. They are generally less reactive than alkyl halides in nucleophilic substitution reactions, but more reactive in electrophilic aromatic substitution. Their stability and reactivity are influenced by the type and position of the halogen atom. These properties make haloarenes valuable intermediates in organic synthesis. Carbon-halogen bond in haloarenes is unique due to the resonance stabilization of the aromatic ring. The bond is shorter and stronger compared to alkyl halides, making it less susceptible to nucleophilic attack. The partial double bond character resulting from resonance contributes to the overall stability of the molecule. This bonding nature is a key reason for the distinct reactivity of haloarenes. Haloarenes are generally resistant to nucleophilic substitution reactions, unlike alkyl halides. This resistance is due to the resonance stabilization of the aromatic ring and the partial double bond character of the carbon-halogen bond. As a result, typical nucleophilic substitution mechanisms like SN1 and SN2 are not favored. Special conditions or strong nucleophiles are required to achieve substitution in haloarenes. Haloarenes readily undergo electrophilic aromatic substitution reactions, such as nitration, sulfonation, and Friedel-Crafts reactions. The halogen atom, being an electron-withdrawing group, deactivates the ring but directs incoming electrophiles to the ortho and para positions. This behavior is crucial for the synthesis of various substituted aromatic compounds and is widely exploited in organic synthesis. Type of halogen atom attached to the aromatic ring significantly affects the reactivity of haloarenes. Fluorine, being highly electronegative, makes the ring less reactive, while iodine, being less electronegative, has a smaller effect. Chlorine and bromine have intermediate effects. Understanding these trends helps predict the outcome of chemical reactions involving haloarenes. Haloarenes are widely used in the chemical industry for the synthesis of dyes, pharmaceuticals, agrochemicals, and polymers. Their unique reactivity and stability make them valuable intermediates in the production of various commercial products. For example, chlorobenzene is used to manufacture phenol, aniline, and pesticides. The versatility of haloarenes underpins their importance in modern industry. Many pharmaceuticals contain haloarene structures due to their stability and ability to undergo further chemical modifications. These compounds serve as building blocks for drugs used to treat various diseases. The presence of a halogen atom can enhance the biological activity and metabolic stability of the drug molecule, making haloarenes crucial in medicinal chemistry. Widespread use of haloarenes in industry has raised concerns about their environmental impact. Many haloarenes are persistent in the environment and can be toxic to living organisms. Proper disposal and treatment methods are essential to minimize their harmful effects. Research is ongoing to develop greener alternatives and effective remediation strategies for haloarene pollution. Detecting and analyzing haloarenes in samples is crucial for both research and environmental monitoring. Techniques such as gas chromatography, mass spectrometry, and infrared spectroscopy are commonly used. These methods allow for the identification and quantification of haloarenes, ensuring quality control in industrial processes and safety in environmental studies. Working with haloarenes requires strict safety precautions due to their potential toxicity and environmental hazards. Proper personal protective equipment, such as gloves and goggles, should always be used. Adequate ventilation and safe disposal methods are also essential to prevent exposure and contamination. Following safety guidelines ensures a safe laboratory environment for everyone. Some haloarenes can have significant biological effects, both beneficial and harmful. While certain haloarenes are used in pharmaceuticals, others can be toxic or carcinogenic. Understanding their biological interactions is important for assessing risks and developing safer compounds. Ongoing research aims to balance their utility with safety considerations. Polychlorinated biphenyls, or PCBs, are a group of haloarenes that have been widely used as coolants and insulating fluids in electrical equipment. However, due to their environmental persistence and toxicity, their use has been banned or restricted in many countries. PCBs highlight the need for careful management of haloarene compounds to prevent environmental and health hazards. Aryl halides, or haloarenes, differ from alkyl halides in several ways. The aromatic ring in aryl halides provides resonance stabilization, making them less reactive in nucleophilic substitution reactions. Alkyl halides, on the other hand, are more reactive due to the absence of resonance. Understanding these differences is key to predicting their behavior in chemical reactions. In synthesizing haloarenes in the laboratory, it is important to control reaction conditions such as temperature, concentration, and choice of catalyst. Using pure reagents and maintaining an inert atmosphere can improve yields and reduce side reactions. Careful monitoring and purification steps ensure the desired product is obtained efficiently and safely. Haloarenes can exhibit isomerism based on the position of the halogen atom on the aromatic ring. Ortho, meta, and para isomers have different physical and chemical properties. This isomerism is important for the synthesis of specific compounds with desired characteristics, especially in pharmaceuticals and materials science. Haloarenes can react with metals such as magnesium to form Grignard reagents, which are valuable intermediates in organic synthesis. However, the formation of Grignard reagents from haloarenes is more challenging than from alkyl halides due to the stability of the carbon-halogen bond. Special conditions and activation methods are often required. Haloarenes can undergo reduction reactions to yield the parent aromatic hydrocarbon. Common reducing agents include hydrogen in the presence of a catalyst or metals like iron in acidic conditions. These reactions are useful for removing halogen atoms and regenerating the aromatic ring, especially in synthetic organic chemistry. Haloarenes participate in coupling reactions such as the Ullmann and Suzuki reactions to form biaryl compounds. These reactions are important in the synthesis of complex organic molecules, including pharmaceuticals and advanced materials. The ability to form carbon-carbon bonds through coupling reactions highlights the versatility of haloarenes in organic synthesis. Degradation of haloarenes in the environment is a slow process due to their stability. Some microorganisms can break down haloarenes, but this often requires specific conditions. Research into bioremediation and advanced oxidation processes aims to accelerate the degradation of these persistent pollutants and reduce their environmental impact. Exposure to certain haloarenes can pose health risks, including skin irritation, respiratory problems, and long-term effects such as cancer. Proper handling, storage, and disposal are essential to minimize these risks. Awareness of the potential hazards associated with halogens is crucial for laboratory and industrial safety. Halogens are used as precursors in the synthesis of advanced materials, such as liquid crystals and polymers. Their ability to undergo further chemical modifications makes them valuable in designing materials with specific properties. The development of new materials often relies on the unique reactivity of halogens. Study of halogens dates back to the 19th century, when chemists first began exploring the reactivity of aromatic compounds. Early discoveries laid the groundwork for modern organic synthesis and industrial chemistry. The historical development of halogen chemistry reflects the evolution of scientific understanding and technological progress. Current research on halogens focuses on developing greener synthesis methods, understanding their environmental fate, and designing new compounds with improved properties. Advances in catalysis and computational chemistry are driving innovation in this field. Researchers are also exploring the use of halogens in emerging technologies, such as organic electronics and nanomaterials. Future of halogen chemistry lies in sustainable synthesis, safer compounds, and expanded applications. As environmental regulations become stricter, the demand for eco-friendly processes and products will increase. Continued research and innovation will ensure that halogens remain valuable tools in chemistry and industry. To summarize, halogens are aromatic compounds with one or more halogen atoms attached to the benzene ring. They exhibit unique physical and chemical properties, are prepared by various methods, and play important roles in industry and research. Understanding their structure, reactivity, and applications is essential for anyone studying organic chemistry. Let's take a quick quiz to test your understanding of halogens. What is the main difference between halogens and alkyl halides? Which reaction is commonly used to prepare iodorenes? These questions help reinforce the key concepts we've covered and ensure a solid grasp of the material. For those interested in learning more about halogens, there are many excellent textbooks and research articles available. Exploring these resources can deepen your understanding and provide insights into advanced topics and current research trends. Staying curious and engaged is the key to mastering organic chemistry. Halogens are not just theoretical compounds, they have practical applications in everyday life. From the production of plastics and dyes to their use in pharmaceuticals and pesticides, halogens are integral to many industries. Understanding their practical uses helps connect classroom learning to real-world applications. Synthesizing halogens can present challenges, such as controlling the position of halogenation and minimizing side reactions. Advances in catalysis and reaction engineering are helping to overcome these obstacles. Mastering these challenges is essential for efficient and selective synthesis of halogens in both research and industry. Green chemistry aims to reduce the environmental impact of chemical processes, including the synthesis of halogens. Using safer reagents, renewable resources, and energy-efficient methods are key strategies. Adopting green chemistry principles ensures that the benefits of halogens are realized without compromising environmental safety. Halogens are versatile intermediates in organic synthesis, enabling the construction of complex molecules through various reactions. Their ability to undergo substitution, coupling, and reduction reactions makes them indispensable tools for chemists. Mastery of halogen chemistry opens the door to advanced synthetic strategies. Here's a summary table of the key features of halogens: structure, preparation methods, properties, and applications. This overview provides a quick reference for revision and helps consolidate your understanding of the topic. Keeping such summaries handy is useful for exam preparation and practical work. Students often confuse the reactivity of halogens with that of alkyl halides or overlook the importance of resonance in their chemistry. Paying attention to these details can help avoid common mistakes and improve your understanding. Reviewing reaction mechanisms and practicing problems are effective ways to reinforce learning. Conclusion: halogens are a vital class of compounds in organic chemistry, with diverse applications and intriguing chemical behavior. Understanding their structure, preparation, and reactivity is essential for students and professionals alike. As research continues, halogens will remain at the forefront of innovation in chemistry and industry. Thanks for joining this exploration of halogens.